Hi, my name is Monica. I am a system administrator at the Research Computing Center at MCW. In this video, I will review different ways in which you can troubleshoot problems with your jobs, specifically what to do when a job either sits in queue and doesn't run, or when it starts running but fails. We will start with the SQ command. This command will help you diagnose why a job might not be running. It allows you to view information about all your jobs that are running or queued. Let's look at the output of this command. The first 4 columns are self-explanatory. The 5th column, ST, shows the status of each job. R means the job is running and PD means that it is in queue pending. The time column shows the time that the job has been running. If the job is still pending, you will see only zeros, as we can see in the last 4 lines in this example. The most important column of the output is the last column. It will show either the list of nodes where the job is running or the reason why the job is queued if it's not running. Here we can see a few common reasons of why a job might be seated in queue. QoS max job per user limit indicates that you reach the number of running jobs allowed per user for the corresponding partition, and that the job must wait until other jobs in that partition finish running. This often happens when you are trying to run more than one interactive job, such as an interactive app in Open On Demand. These applications will have sys- in the column name. In this example, we can see that I have 2 interactive apps in my queue. One is running on compute node 58 and the other is seated in queue. You are only allowed to run one interactive job at a time. That is the reason why my second interactive job here is in queue and not running. This reason code can also appear when running array jobs. In this case, you must wait until other jobs from the array finish running before the pending subjobs of the array can run. Resources. This code indicates that the job is waiting for the requested resources to become available. Make sure that you don't request more resources than what you need, because if you request too many resources, there is a higher chance that some of them might not be available when you submit the job and that it will sit in queue for some time. In this case, you can either reduce the number of resources that you requested if you think that you might have requested more than what you need, or you have to wait until the resources that your job needs become available. Dependency. This job will appear if a job dependency is not yet satisfied. You can learn more about job dependencies in our video about creating an advanced SLURM script. The link to that video is in the comment section down below. Another common reason for a job being queued is when a node is being reserved for maintenance. That will happen if you submitted your job close to the maintenance window, and if allowed to run, it wouldn't be able to finish before the maintenance starts. In that case, leave your job in queue and it will automatically start running when maintenance finishes. If a maintenance window is approaching, you will see a message when you log into the cluster through SSH. This message will appear 7 days before maintenance, and it will look like this. Please be sure to check any messages at login. Some of them will be important and can affect your job submission. If none of those reasons explain why your job is queued longer than expected, contact us to the email provided here with your job ID and we will look into it. If you send us a copy of your SLURM script, that will help us diagnose the problem. Be aware that your job's wait time will be affected by their priority. This priority is based on many variables, including job size, the time a job is already been in queue, fair share, etc. These factors are balanced to ensure that small and large jobs can run efficiently, also that frequent and infrequent users have a fair chance to run jobs, and overall utilization is balanced among all users. The command sprio is used to view the priority of pending jobs. In the example here, we have the command run twice on a pending job. As you can see, the priority increases as age increases. to help ensure that jobs don't get stuck indefinitely in queue. Age is the length of time that your job is seated in queue. As you would imagine, jobs with higher priority will run first. Fair share is an important factor, and it's a measure of how much a user has been using the cluster over the past week. The value is lower for users that have used fewer resources recently. Priority increases as fair share decreases to ensure fair use of resources. This is another reason not to request more resources than what you need when you submit jobs. If you always request a lot of resources, your fair share will increase and your priority will decrease, so jobs will take longer to start running. You can use the following command to see how many jobs are ahead of yours in the corresponding partition. I will copy this command in the comments below. Replace GPU by your job partition. In this case, our job of interest is scheduled to run on a GPU node. And the number at the end by your job ID. The output will highlight your job ID, and it will be easy to see how many jobs are ahead of yours in queue. In this example, there are 6 jobs ahead of our job of interest in the GPU queue. The -P flag is used to print only jobs from a specified partition, in this case GPU. These two flags, sort and white, tell the command to print jobs in descending priority, so showing those with higher priority first, which are the ones that will run first. This part of the command tells Bash to add line numbers. And this part highlights our job ID for better visualization. Let's learn now how to troubleshoot jobs that start running but fail. A job can fail immediately without producing any useful output for many reasons. One of them can be a bug in your code. Looking at the log file will help you find out if that's the case. The name of the log file will be based on your Scratch output option, or if no output option was specified, it will have the format shown here. In this example, the log file tells us that we are trying to access an image file that does not exist in the directory where the job is executing, and we need to fix the path or the name of the file. Make sure that the files that your job uses exist and are located where your script expects them to be. Also, be aware that jobs are run in compute nodes, which have access to Scratch but not to your home or group directories. If your log file shows a command not found error, it most probably means that you forgot to load the corresponding module or loaded the wrong module. Here, I probably forgot to add a line in my script with module load FSL, which is the program that contains the command bet. Storage limits can also cause read and write errors. If your Scratch is full, your jobs will fail immediately. Your interactive jobs might also fail if your home directory is full, because they need space there to save temporary hidden files. You can check how much storage you have available with the mydisks command. If you run jobs in Open On Demand often, eventually your home directory will get full of some temporary files that are created every time you start an on-demand job. These files are hidden, so it's easy to miss that your home directory is getting full. If your home directory is full, check for large files that you can clean up. If you don't see any files in there, include hidden files in your search with this flag. Using Conda also generates hidden files that can fill your home directory without you noticing it. Specifically, look for large file sizes. Some common hidden files or folders that may cause problems would be .cache, .conda, .share, .nextflow, etc. Consult with the RCC if you have any questions about deleting the contents of these hidden folders. If your job stopped unexpectedly and the log file didn't provide helpful information as of why it failed, you can run the SF command. This command is used to check the efficiency metrics of a finished job. but it also serves to check the exit state of a failed job. A common failure is the job running out of memory. To fix this issue, increase the amount of memory and resubmit the job. If you don't know how to request more memory, I suggest that you check our video on how to write a simple script. There I explain how to request resources. A link to that video will be provided down below. Another common failure of running jobs is a job timeout. This means that the job hit wall time before it finished, and you need to request more time or shorten the simulation before resubmitting the job. If the state is just failed, then most probably there's a bug in your code. You can obtain more information by looking at the log file, or send us your SLURM script and the output log, and we will help you diagnose the issue. You can also use XD mode to troubleshoot a failed job. I will explain soon how to use this tool. Remember the value highlighted here, as well as the job ID, as you will use them to search for your job in XD mode. This is an open source tool that can be used to monitor and troubleshoot your jobs. It processes data overnight, so you have to wait until the next day to troubleshoot your job using this tool. To access XD mode, you must follow the link shown here. This link is also included in the description below. Then click Sign in the upper left corner. Then in the next window, click the MCW logo. You will then be redirected to a login page where you should enter your MCW credentials. Select the job viewer in the upper menu. Then follow the on-screen instructions to search for a job. Enter the values that I mentioned earlier from the output of the SF command in the Quick Job Lookup section. Cluster name and job number. Make sure to select jobs in Realm and then click Search. Your job will appear in the results area. Click on Save Results at the bottom. Your job search will appear in the search history. Expand the directory and click on Accounting Data. You will see accounting information about your job, including the exit code and state and the requested resources. If you still don't know why your code is failing and none of the previous tools help you figure out what is happening, you can run an interactive job to debug your code. Use srun followed by the sbash options that you would use in the submission script, followed by --pty bash. Then you can execute line by line the code in a compute node and see where it fails. While you are executing commands in your interactive job, you can precede your commands with time, as shown here, to see the time that each command takes to execute. Another option for diagnosing what is happening when a running job stops unexpectedly is to resubmit it. Then you can run the following command. This will place your shell on the head node of the running job. In this example, my running job is executing in compute node number 9. From there, you can run some commands to examine what is happening with your job while it runs before it crashes. One of those helpful commands is stop. This tool is used for real-time monitoring of system processes and resources. The -I flag will hide idle processes to limit a bit the information shown. This is an example of what the output of top looks like. In this example, there are a couple of things showing that the system might be overloaded. So, jobs running in this node could potentially take longer than expected to run and unexpectedly hit wall time. First, the load average is 49, higher than the number of CPUs, which is 48 in all compute nodes. This means that in average, all cores are being used and some processes are waiting for CPU time. We can also see that at this moment, 99.4% of the CPUs are being used. This is by itself not bad. We want the system to be used as much as possible and we don't want CPUs to sit idle. But here we can see that many processes are using 100% of the CPU, and so it is inevitable that some will have to wait to execute. We can also see that from the 679 tasks in this node, only 50 are running and 629 are sleeping, waiting for the CPU to become available. To exit the top command, press the letter Q in your keyboard and top will quit. Now we can type other commands. Another useful command is strace. This command traces interactions between a program or command and the operating system, including notifications or events that can interrupt the normal execution of a program. I can run it on a specific command that I know is failing but don't know why, or on an executable script. Right after the word strace and before the program that I want to trace goes the list of flags for strace. One very useful flag is -O, which redirects the output to a file. Sometimes the output can be long and it will be easier to read in a file. Some very important information will be printed in the command line. In this example, it printed the error that made the program exit. A command in line 29 of my script was not found. This is because I didn't load the corresponding module that uses that command. If I want to investigate more details about the system calls, I can look at output.txt. The failed only flag tells strace to print only those system calls that returned a failed status, to reduce the number of lines that are printed. If your program is a multi-threaded application, the -F flag can be useful to trace child processes as well. Another useful flag is -T, which will print timestamps on each system call. Or -V, which provides verbose output, including arguments and return values. Now we can exit the interactive shell and go back to the login node. Finally, if you are at loss on why your job is failing, please submit a ticket by emailing us to this address. If you give us as many details as possible on how and when your job failed and send us your script and log file, we will be able to help you better. I hope this troubleshooting video has been helpful, and I will see you in the next video.